Hello, hello. Oh, thank you. Well, I'm willing to work out some of the kinks in the class. It's 11 o'clock. I'm willing to work out some of the kinks in the class. This might not be the way we hand in homeworks. To be honest with you, I haven't collected homework in about 10 years from my students. But like I said at the beginning, I found that I should collect homework. Or I realized my students didn't do it. And I can't speak for you in any individual sense. But in the average, it was clear that that was happening. And I really find it important to do that homework. Again, Arturo, Christopher, Jingyang. We may revert to a homework box or something like that because we can't do this every time. Okay, so we're going to do one more integral today. I want to talk about it. I think this integral is important. Okay. So we're in chapter 15. Pardon me for this delay. 15.2 is double integrals over general regions. 15.3 is area by double integration. And 15.4 is double integration in polar coordinates. I will actually be assigned, I've already assigned the homework for 15.2, 15.3 right before I got here. So it'll be in the assignments. And 15.4 will be assigned also because I'll be able to talk about it on Friday. I can only speak to their accents. I don't know where they're from. So it'll be a pretty big homework. It'll be a pretty big homework. area of a circle. Let's consider the area of a circle. Yes, sir. I wasn't pleased with the way this process went. And that's through no fault of your own, it's my own fault. So I'm thinking about it.
If you have it set up in advance, then everyone when they walk in can put it up and it typically does not pass.
Yeah, the fact is I should have had it. So if we can do this every time, just 3 piles, Arturo, Christopher, Jing Yang, you just make those 3 piles because you might get here before me and want to escape, as some people did. You can just do that and escape if you wanted to. So let's just do 3 piles, Arturo, Christopher, and Jing Yang. Then we're okay, right? And then you'll have some time to discuss, instead of trying to hand it in during discussion section, or worse, having to come to the math department when you have all these other draws on your time, okay? So I'm trying to avoid all of that. Arturo, Christopher, Jing Yang. Arturo, Christopher, Jing Yang. Area of a circle. Area of the interior of a circle. Area of a disk. Okay, area of a circle is probably incorrect. I should be more precise. Area of a disk whose boundary is a circle of radius, okay, of radius r. Capital R is going to be the radius of this thing. Now, like I said, a lot of what we're going to do is talk about problems you know, whose answers you know, and try to introduce new techniques to this. So here is a circle, or my terrible attempt at drawing a circle. And we know that the circle of radius r is given by the implicit form. This is an implicit form. X squared plus y squared equals r squared. Okay? We're going to study another form of the curve called the parametric form when we get to chapter 13, which will be very important. This is implicit. We can write it explicitly for y in terms of x, or x in terms of y explicitly. Sometimes either one of those is useful, but this is an implicit form. Okay? So how do we calculate the area of a disk of radius r? Well, we know what this is, right? Area equals pi r squared. We know, right? We were told at some point that area equals pi r squared. Of course, this hides something. What is pi? Well, we were told what pi is, right? We were told what pi is. So we've been told everything. We've been told everything, which is a little dismaying because mathematics, you should not be told anything. You should be able to reconstruct it from scratch. Okay? So in particular, what do I mean by pi? Okay? So what is pi? Pi, well, if the area of this object is pi r squared, and this I know is r, and then I make a square over there, the area of this square is r squared. So area of the square is equal to r squared. And so what you see is that pi is equal to the area of the circle divided by the area of this square, of one of these squares. Okay? And pi is 3.14. So that's what pi is, right? That's what we mean by pi. Okay? That's what it's defined as, or a way to define it if you wanted it. Now, what is it equal to is another question, right? And thousands of years of human labor have been involved in how you calculate what the value of pi is. How do you do that? Okay? So let me just make a comment about pi. Pi is 3.14. For the longest time, that was very close to 22 divided by 7, 3 1/7. Approximately. That's a decent approximation for pi. And so that tells you that the area of the sum of these 3 segments is 3 1/7 the area of this square. It's less than 4. It's more than 3. Okay? Well, that helps you a little bit, I hope, gives you a sense of what pi is. But now how do you compute it? How do you compute the thing? Well, I know how to compare it with the area of the square. I put a ruler here and I put a ruler there. So I'm given a particular square, okay? And I do this construction. I know how to draw a circle. And now I want to compute pi. So I want you to put yourself in the mindset of a person maybe 4,000, maybe, the Pythagoreans 3,000 years ago, Was it? Okay. How would you go about and compute pi? Well, if I know this, I want to figure out this. To compute pi, I better try to figure out that. Okay? And maybe I don't need the whole circle, I just need one of these segments. And therefore, I need to compute the area. So I want to compute the area. So you can say, well, look, area of the circle, let me write it, A sub c, is equal to, well, we've talked about what area is now in terms of double integration, right? So it is equal to the double integral over the circle of dA. And I want to emphasize to you over and over and over again that the real way to do this, the actual way to do this, is to go to that circle, to cut it into small pieces, ideally small rectangles or small squares, to measure the area of all of those squares and add it all up. Okay? And so if you are to do this, you imagine that what you're doing is taking this circle, and here I'm going to cut it up a little bit. Okay? You're going to do this. And here is one partition associated with doing that double integral, a partition not in the limit that the partition size goes to 0. I better make them delta A's. I want to make them sort of rectangles, okay? Okay? And so, etc. down here. Okay? And so now you can go do this, right? You can go do this. And what you do is you literally take a piece of paper, literally cut out a circle, literally, not figurative, literally, right? Go cut it out and then cut some strips, right? And calculate the height, maybe the area of these strips or whatever you're doing, and there you'll get an approximation for the area of the circle. Okay, you're going to get an approximation. You're going to get an approximation for it. But when you have that approximation for that, then you know the numerator, and then you divide by the r squared, which I can calculate. That's easy to do because I know how to calculate r, and I know how to multiply by another r. Done. I just use a ruler. Okay? And then you have an approximation for pi. That's how you do pi. You don't wait till somebody tells you what pi is. Okay? So when I was a kid, I actually computed pi myself because I'd heard about this thing called pi. I was little, and I took a measuring tape, and I started measuring circles, and I did my little, division, and I'm like, oh, there's pi. Oh, there's 3.14, and I think I got to 3.14. But you actually have to do that computation. That's actually how pi is computed. It's not, there is this constant, which is truly that, but it has to be computed. You're going to be like, why the heck is he going on this? Probably a lot of you are like, why is he going on this crazy tangent, right? Well, you say, Professor, I can just do the integral. Okay, let's do the integral and see what happens when we do the integral. And I'm telling you this because there's a real deep philosophical point here. Yes? Well, like I said, there's no such thing as negative area, right? So that doesn't make... Like I've been trying to beat it out of you. There's no area.
Like if you have a polynomial function that dips below, and we take the integral from a to b, and part of that integral includes the low part, we end up getting area knocked off, don't we?
But there's a circle. It's got positive area.
Yeah, but
that's why I said in the last few lectures, that metaphor. And by the way, I'm glad you brought this up because I'm sure more people have this in their mind. The metaphor that the integral is area is going to confuse you if you continue to use it in this class. Okay? The integral is the numerator of the average. When you want to compute the average of a function, the integral in one dimension is the numerator of the average. Okay? We are doing the double integral. This is an area. Each of these things is a positive thing. Right? I put a tile on it, right? I can put a little tile on it, that's got a positive area. These things are a bunch of positive areas. So that's not going to arise, okay? And so I do want you to stop thinking about the integral is equal to the area. Okay. But it'll come with examples. I have to unteach you something and maybe teach you something in the process to replace it. Okay, so how am I going to do this, right? How am I going to do this right now? Well, folks, I'm going to use Bielow's surefire technique for finding the regions of integration, okay? So Bielow's surefire technique for finding the region of integration asks you to begin by writing area, which is equal to that, area, which is equal to that, but by choosing an order for Fubini's theorem, okay? Now, I tend to go with y first. In this case, the problem is completely symmetric. Doing x first or doing y first would have been literally exactly the same. So you're going to do y first. Y is going to go from y min as a function of x to y max as a function of x, okay? dy, the number 1 is sitting there. And then I put parentheses around that because I want to emphasize you do this first, and then you do this, okay? And then x is going to go from an x min, which is just a number, to an x max, which is just a number. And then you take your chalk, and you put it on the figure. And you draw a vertical strip, because that corresponds to the first integral, the one inside the parentheses. It says go along the y direction first. So these are your strips, okay, that are associated with that first integration. And then you go to the lowest point in each strip, and you put a circle there. That's the lowest point. Okay? And then you go to the highest point in each strip, and you put a x there. That's the highest point. Okay? And then you connect, sorry, there's the lowest, there's another lowest. And you connect the dots, the circles, and you say this curve is where y max of x is. This curve is where the y max of x is. Yes. No, y min, right? Thank you. I saw it and you're like, just communicated in my brain. Thank you. Y min, that's y min of x, right? Y min of x. And this curve is where y max of x is. So now you know which curves they are. You just got to figure out the algebraic expression for those curves. Okay? And of course, I have over there, one of the first things I wrote, is the implicit expression for y of x. And we know that the explicit expression is pretty straightforward. Okay? So what you do is you solve for y. So using x squared plus y squared equals r squared, I rewrite it as y is equal to r squared minus x squared to the power of 1/2. And when you take a square root, you must always include the positive or negative options at the start. Okay? You may have to discard one option because of other considerations, but always start with getting them there and then discard later. And it's quite obvious, I hope it's quite obvious, that this is the negative square root and this is the positive square root, right? That's the negative and that's the positive. So y min of x equals negative square root of r squared minus x squared. And y max of x equals positive square root of r squared minus x squared. Okay? Now, that's the first piece of it. Now we have to find x min and x max. And the thing to find x min and x max is to recognize that x is constant along each vertical strip. This is a curve. Ideally, it was straight. A curve of x equals constant. This is the x equals 0 curve. This is the x equals whatever. Okay? And you go to the strip at the leftmost value, the leftmost strip, the smallest x-most strip. Say it 5 times fast. There's a strip over here, and it limits to having an x value of x equals negative r. So you do that, okay? I don't even know how to write that algorithm, okay? It's that process of, in your mind, you go, bam, okay? X min equals negative r, and then you go, bam. X max equals positive r. And if you hear sound effects in your head, it's good. This keeps you company. Okay? And therefore, that's how you get those limits. And so now we are left with area is equal to the integral from negative r to r, the integral from negative square root of r squared minus x squared to the positive square root of r squared minus x squared. You integrate with respect to y, and then you integrate with respect to x. Ta-da. Okay. Now, aside. Here's an aside. I'm trying to teach you little things that you were actually taught, but you may have forgotten. Okay? If you integrate a function from negative a to a, f of x, and f is a symmetric function, and you integrate with that with respect to x, that is equal to twice the integral from 0 to a of f of x dx. What do I mean by a symmetric function? A symmetric function has the property that for all x, f of negative x is equal to f of x. Okay? So what example? A symmetric function is a function that looks like that. It looks exactly the same left and right if you flip from here to here. Okay? What are some examples of symmetric functions? Well, e.g., y equals x squared is symmetric. Okay, so actually let me write f of x. Don't write it that way. Right, f of x equals x squared is symmetric. Okay, yes? I'm sorry, yeah. No, I can't, because it's the backboard. So I'll go over there. No worries. Okay, so e.g., f of x equals x squared. That's symmetric. Okay, how do I know? How do I know? Well, what you do is you substitute f of negative x in there. So that means wherever you see x, you put negative x. And that means that's negative x quantity squared. That's what you're asked to do. And that's equal to, well, negative squared is positive, so that's equal to x squared. And that x squared is also equal to f of x. So f of negative x is equal to f of x. It's a symmetric function. All the even powers are symmetric. Squared, fourth, for exactly this reason, right? You get rid of the negative. Another example is cosine. F of x equals cosine of x. Well, you do the same thing. F of negative x equals the cosine of negative x. Right? But you just remember from the definition of cosine, this is cos x, which is f of x. Okay? Cosine looks like this. When drawn properly, it looks better than that. Okay? And this is completely symmetric left and right. Okay? And all that statement is a statement of the fact if you integrate from any 2 points equidistant or symmetric around the origin, okay, the area under the curve here is equal to the area under the curve there. Despite the fact that I told you not to think about area. Okay? Since we're here, I just want to point out, I'm going to move this board down now, if you don't mind. You guys are done with this on this side? So an anti-symmetric, so this is another cloud of knowledge. The integral from negative a to a of f of x dx equals 0 for anti-symmetric functions. Okay, for all anti-symmetric functions. Okay? And an antisymmetric function has the property that f of negative x equals negative f of x. That's an antisymmetric function. Okay? So now we'll do an example. E.g., f of x equals x. It's an antisymmetric function. Let me plot it. It's the kind of the nice example, okay? So an antisymmetric function is not going to be symmetric left-right. You're going to got to go flip this way and then flip this way. It's a double flip. Da-dee, da-doo. Okay? Well, what is f of negative x? Well, that's negative x, which is equal to negative x, which is equal to negative f of x, which is equal to negative f of x. F of negative x is negative f of x. Or f of 3 is 3, and f of negative 3 is negative 3. It didn't matter that I chose 3. It could have been any number. Those are antisymmetric functions. And what's another antisymmetric function in the spirit of our colleague at the bottom of the board over there? Sine, right? Sine is antisymmetric. In fact, the symmetric, antisymmetric, you can basically break up all functions into a symmetric part and into an antisymmetric part. All functions, it's pretty straightforward how to do it. In fact, for those of you who need some more to think about how you can break up any function into a symmetric part and an antisymmetric part. Yes? Even and odd? I think of them as even and odd. Yeah, I think of them as even and odd. Yeah. I mean, if that helps you, I wouldn't say, yeah, yeah. Not wrong at all. Even and odd. Odd seems so disparaging, however. Okay. That was an aside. Took a little longer than I thought, but all my asides will take longer. I hope that adds to your toolkit. When you have that in your toolkit, you can actually do integrals more rapidly. Okay. The function constant, the constant function, is a symmetric function. Does that make sense? Right? Just draw it. Flip it left, right. It looks exactly the same. This question is asking you to integrate from negative to positive a symmetric function. Same value, right? So this is going to equal the integral from negative r to r of 2 times the square root of r squared minus x squared. As you can see, or I hope you see, I'm moving into second gear here. Okay? We're using that information. Now this too, the x squared is a symmetric function. The square root is a symmetric function. This thing is a symmetric function, right? In fact, if you were to think about it, this is really the curve that is the upper boundary of the circle, right? And then you can see that the upper half circle is a symmetric function. And so this is equal to 4, because I get another factor of 2 from here and a 2 from here, times the integral from 0 to r of the square root of r squared minus x squared dx. Okay? So this is the integral I have to do. And I claim that I'm going to get a number here. Okay? That's going to be the number, which is the area of the circle. And then when I divide it by the area of the square, r squared, I'm going to have pi. Okay? So let me just do something for fun, because you don't have to think this way, but I'm trying to not just show you how to do simple computations, which you might know. I'm trying to help you interpret what you're doing, maybe think about them like how I think about them a little bit, okay? So don't ever do this step, okay? This is a step that I do for you, okay? And it's a simple step, but nonetheless, it has interpretation, it has meaning. Let x equal r times u. I am doing a u substitution in this integral, okay? Let me let x equal r times u, okay? That means dx, r is a constant. R is just the radius of that circle, 5 meters, 2 centimeters, whatever you want. That means dx is r times du. Okay? When you do the u substitution, you must change the variable, you must change the differential, and then you must change the bounds of integration. So when x equals 0, which is the lower bound of integration, u is equal to 0. Just substitute x equals 0 here, divide by r, you got u equals 0. When x equals r, u is equal to 1. Okay? So now let me make this substitution in there. So the area is equal to 4 times the integral from 0 to 1 of the square root of r squared minus r squared u squared. Dx is r du. Is that good? R du. That's what I said dx is. And then I'm going to pull out the common r from both of these factors and take its square root. So I'll have a factor of r and I have a factor of r. So this is going to be 4r squared times the integral from 0 to 1 of the square root of 1 minus u squared du. Okay? Yes? A little louder, I can't hear you. Okay, so I got a 2 from this symmetric function, and then I got another 2 from this one. So 2 times 2. Okay? Well, but what did I say? I said the area of this circle divided by r squared has to equal that pi thing. So this has to equal pi. In other words, I'm going to go back over here, over here, over here, over here. So area of circle divided by r squared is equal to 4 times the integral from 0 to 1 of the square root of 1 minus u squared du. That's got to be equal to pi. But I still haven't computed pi for you, right? I still haven't computed pi for you. And so what do? Well, we go to 21b. We go to 21b, and we have to do another u substitution. Okay? And so what's the u substitution? Let u equal the sine of theta. That's the substitution you would do on this one. Okay? And that means du is equal to cosine theta d theta. That means when u is equal to 0, theta is equal to 0, because the sine of 0 is equal to 0. When u is equal to 1, theta is equal to pi over 2. And so this thing is equal to 4 times the integral from 0 to pi over 2, the square root of 1 minus sine squared theta times cosine theta d theta. Okay? And the square root of 1 minus sine squared theta is cosine theta. So this is 4 times the integral from 0 to pi over 2 of cosine squared theta d theta. Okay? So now we can do another trig substitution to get this, but I don't want to do a trig substitution to get this one. Okay? What do I want to do? I want to show you something else. Maybe it'll edify you a little bit. Okay? I want you to sketch the function cosine squared. So cosine squared is a positive function that looks like this. This is pi over 2, and this is pi. How do I know it? Well, cosine goes down and back up. Down to pi and then goes back up to 2 pi. Okay? And just for a moment, if you don't mind, I'm going to sketch sine squared also. Sine squared is a function that looks like this. Right? And what do we know from Pythagoras' theorem? We know that cosine squared plus sine squared is equal to 1. So the sum of this function and the sum of this function is always 1. Okay? So we know that the sum of these two functions is 1. But if you look at them, and you can see this quite readily, or you remember it from the definition of cosine and sine, that cosine is only a shift of sine. And sine is simply a shift of cosine. So you see that these this bump up function is simply a shift of this function. So pause for a second. Now think about that. If two functions are just shifts of one another, and I want the average, I'm looking for the average of this function. And this one is just the shift of this, the previous one. That means the average of this function must equal the average of this function. They must be equal, right? It's just, if I have two buildings, the average height of the two buildings doesn't matter if I had them right and left versus left and right. Okay? The average height is the average height. Same thing with, that was just a shift. Okay? So the average value of cosine squared is equal to the average value of sine squared, which means that the average value of cosine squared is equal to 1/2. I just put that for average. And because if this is cosine squared and this is sine squared, and you take the average value of both sides and they're equal, then they must be, and they add up to 1, they must be equal to 1/2. So the average value of sine squared theta is also equal to 1/2. Okay? But what did I say about the integral? So this is, okay, let me say this again. What I've done for you is a very simple calculation. I'm doing a very simple calculation. Completely, I acknowledge it. It's a trivial calculation, really. So these couple substitutions, you had 21b, you can do all this stuff. What I'm really trying to do is interpret all of these steps of this calculation in a larger context, okay? Nothing I've done here is particularly fancy. But what did I say about the integral? I said the integral of a function, right? I said the integral of a function from a to b of a function f of x dx is equal to the average of that function, and I should divide this by b minus a. Right? Integral of the function divided by the length of the interval is the average of the function. But the integral of the function from a to b of f of x dx is equal to, therefore, b minus a times the average value of the function. I just multiplied the denominator across. So here's the integral from 0 to pi over 2 of cosine squared. That must equal the average value of cosine squared. There's the 4, just coming down from the right. The average value of cosine squared is 1/2 times pi over 2 minus 0, the length of the interval. And therefore, this must equal pi. Now, some people are smiling because that was kind of cool. Maybe some people thought it was cool. Some people are like, I'm done with this calculation 15 minutes ago. It is a little cool. It shows how things tie together, how they all hang together. But now if I were to ask you, what is pi? Do you yet know what pi is? And so this is one of the things that I want to emphasize. You don't know what pi is yet. Pi is still just this ratio. And all I've showed you with this whole pretty calculation and a bunch of u substitutions is that all of this calculus hangs together properly. That it hangs together properly. I hope I've showed you a little bit about antisymmetric and symmetric functions. I hope I've made you think about how you use the average to understand what you're doing. But ultimately, you should still be dissatisfied with me because I haven't showed you what pi is. The only way to compute pi is to actually go and do the Riemann sum that the integral demanded of you in the first place. The rest of this is symbolic manipulation. You're actually not doing the calculation. The only way to compute pi is to take a big compass and cut out a big circle and then chop that circle into tiles and count the number of tiles. Count those areas. That's it. And that's the way you got to do it. Okay? And that's the way your calculator does it when you just do that thoughtlessly. Thousands of years of work went into that. Okay? Thousands of years of thought. And that's what I'm trying to emphasize to you, is that although sometimes we do all these substitutions and these manipulations, they must hang together, or else the math wouldn't make any sense. But it should still leave you a little dissatisfied as to what pi is. Okay? So now if I were to ask you, given, say I would ask you on an exam to estimate the value of pi, I would say, well, let's try to do the value of pi. Let's try to figure it out, right? Let me try to figure it out. And what I would say is you should draw boxes. You should do what you would have done if you were in elementary school. And what you would have done in elementary school is you would have taken maybe just the quarter circle, because you're like, I don't need to deal with the whole circle. And I would make that a radius 1 meter. And then I would draw that square, and maybe I would draw a rectangle here, and a rectangle here, and then a rectangle here, and say the area of these 4 things together is a little bit more than pi over 4. Okay? Because it's a quarter of the whole area. Okay? Here's another way to calculate pi, just for fun. Okay? So you guys are going to the bars on Saturday nights because you're all 21, right? And we play darts. Okay? We like to play darts. So, and you're a terrible dart player because you're like me. I don't get to play darts very much anymore. And you have a square on a wall. Okay? And you can only throw within that square, and you draw a circle within that square that fits the square perfectly. Okay? The area of that square is 4 times the radius squared of the circle. Right? The area of the circle is pi times the radius squared of the circle. Start throwing darts randomly. After throwing about 1 million of those darts, because you've got a lot of time on your hands, you go and count the number. So you say you've thrown 1 million. You take the ratio of the number that landed inside the circle to the total, and that's equal to pi divided by 4. Because that's the area of the circle divided by the area of the square. That's another way to calculate pi. In fact, computers use that method. That's called the Monte Carlo method. Okay? So those methods are actually very common in computer algorithms nowadays. So has anybody computed pi by hand before? No, you just don't do these kinds of things anymore, do you? I could give you slide rules. Yes? Did you? So now have you used it to compute pi? Okay, good. Yeah, go ahead.
One of the assignments is to compute pi using the Monte Carlo method.
Oh, it is? There's your answer. So you choose 2 random. Okay, here's the trick. Choose 2 random numbers. It's so easy. Choose 2 random numbers, the x coordinate and the y coordinate, and then just figure out if those 2 random numbers fall within the circle or outside the circle. Do it a bajillion times and divide by the total number of dots you've chosen, and that'll approximate pi. I don't know how quickly it converges to pi though, but it's a useful calculation. Okay. So this was one example. I just did one example, but I did 1,000 things in this one example, right? I took you in all sorts of different directions. Okay, I hope I contextualized all the different things you've learned by learning calculus up to 21B. Okay? And I hope I've made your ECS 30 assignment super, super easy. Okay. The class is extremely quiet today. I don't know if you're just getting over that quiz. Okay, so I think I've done enough about 2-dimensional integrals in Cartesian coordinates. Okay? I haven't done a lot of examples using an f of x and y. It's just computationally more involved, but ultimately it is what it is. Let me make one comment about the types of questions you find in calculus books. The types of questions you find in calculus books will often ask you to change the order of integration. Okay? The idea there is that they're trying to teach you the geometry of the boundaries. They're trying to teach you to think about the boundaries. It's not really about the calculus to change the order of integration. It's really about algebra and geometry. Okay? There are some of these questions in calc books that if you did the y integral first and then the x integral, you could never do it. But if you did the x integral first and the y integral, then you could do it. And they're like, hey, look, changing the order of integration is a useful way to actually solve the integral in reality. And that's a lie. That is the calculus book lie to its children, okay? It is not true. Those questions are so contrived, so like pieced together in some, you see those functions, you're like, when am I ever going to come up with log reciprocal of something? These are contrived questions, okay? So you don't actually bump, it's never useful, or almost never, except for the calculus book questions. It's very rarely useful to change the order of integration if you can't integrate it one way based on the function that's inside, okay? I'm saying this because I assume you've looked at these types of questions already. But nonetheless, it's useful to do that as a few exercises for your homework to give you adeptness with changing the order of integration. That's why I assign them, okay? But they're not the kinds of questions you'll find on my exams, okay? That's what I'm trying to tell you. Or nor are my quizzes. Do I have a question? You guys are really like low energy today. I'm going to have a coffee machine, a little espresso machine for y'all. So you can come in, nice and espressoed up, stretch. I got 5 minutes. We're going to do all polar coordinates in 5 minutes, okay? Polar coordinates in 5. Go. Section 15.4, I'm not going to do polar coordinates in 5. We're going to do it today, and we're going to do it on Friday, okay? But we will finish with polar coordinates on Friday. Section 15.4 is how do you deal with polar coordinates? How do you deal with polar coordinates? What if you had your functions expressed in polar coordinates? You should ask the question, when would I want to have my functions expressed in polar coordinates? I like Cartesian. Don't just give me polar for no reason. And how do we envision using polar coordinates to simplify our computation? That's it. So polar coordinates to make my life easy. Okay. Polar. Okay. So I'm just going to start by talking about polar coordinates again. You guys know what polar coordinates are. You've done it already, but let's just dust the cobwebs off of that, okay, in the last few minutes. So any point in R2, there's a point. It's either represented in Cartesian coordinates, x, y. And what we mean by Cartesian coordinates is you consider these curves, these straight lines, they're curves ultimately, and you say, you go along this line, a distance x, and then you go up this line, a distance y, or vice versa, and that'll get you to the point. So you go east 2 steps, and north, in this case, maybe 4 steps, okay, to get to the point we're seeking. And this coordinate system has a property that there's a right angle over here, and there's an origin over there. These are all the things you need to have to make sense of this computation. Of course, there's another representation, and the other representation is to recognize that instead of telling your friend walk east 2 steps and north 4 steps, tell your friend to walk whatever number of steps straight to the point at an angle theta. So this is called r. This is the straight line distance from the origin, an agreed upon origin, to the point P. And this theta is the angle between an agreed upon axis. We choose x to be our agreed upon axis. In an agreed upon direction, we choose counterclockwise to be agreed upon. And it tells you how to get to that point. Okay? Of course, when you draw it this way, bam, the triangle screams at you. Okay? And the triangle says, oh, look at this. If this is x and this is y, clearly r is the hypotenuse of the triangle. So by Pythagoras' theorem, r is equal to the square root of x squared plus y squared. That tells you, if you know how far to go east and how far to go north, I'll tell you how far to go in the straight line distance. Okay? Of course, theta, okay, we can realize that the tangent of theta is opposite over adjacent. Toa. Opposite over adjacent. Brain hiccup there. I'm sorry about that. The tangent of theta is opposite over adjacent. Okay? And so that means that theta is the arctangent of opposite over adjacent. Okay? And this is the coordinate transformation from Cartesian, these are called Cartesian, to polar coordinates. Okay? This is the transformation. And let me just tell you about the structure of coordinate transformations, because we'll be doing more of them in this class. When you're in a two-dimensional system, that means you need two pieces of information to tell you where you are. Okay? If you do a different coordinate system in 2 dimensions, you still need 2 pieces of information. Right? You need to know distance and angle. You need 2 pieces of information somehow. Okay? So to get those the transformation will always be 2 equations. You start with 2 variables on the right-hand sides of those equations, and you have this is an explicit transformation, so you have 1 and 2 variables on the left-hand side. So you have 2 equations. Is this the first time my mic's been? You heard me through the mic? Oh boy. Well, I don't know if it got recorded. Oh well. Don't want to see it anyway. This is the transformation from Cartesian to polar. There is also the inverse transformation from polar to Cartesian. That would be 2 pieces of information to 2 pieces of information. So it's now 2 equations, 2 equations. I'm telling you this because you go in 3 dimensions, you need 3 equations and 3 equations. Okay? And it starts to get complicated if you're not paying attention. So I just want to warn you as we go forward, what's the transformation in the other direction? Well, we can see that x divided by r is the sine. Why did I call that x? Oh! You guys just leave me there to suffer. Because now it's videotaped. This is going to be embarrassing. I got to totally chuck this one. If I do something that boneheaded, can you at least make the face like I'm a bonehead face? Like, just don't even raise your hand. Just look like, do something like that, okay? At least, so I'm trying to look at your faces to see if at least you're following me, okay? But give me the bonehead look, okay? That's fine. I can handle that. Okay? I'm confident enough that I know what I'm talking about that I can handle bonehead typos. But I don't want you to suffer bonehead typos. I apologize for that. No, opposite. But this was correct, right? Because I did opposite over adjacent. I just didn't see x, so I apologize. Please tell me when I do something silly like that. The sine of theta is y over r. That means y equals r sine theta, and of course, x equals r cosine theta. The structure of a coordinate transformation has one coordinate system on the right-hand side, the other coordinate system on the left-hand side, and the number of equations is the number of dimensions you're in. This is the polar coordinate on the right-hand side, Cartesian on the left, 2 equations, we're in R2. Cartesian on the right, polar on the left, 2 equations, we're in R2. Okay? That's the structure of these transformations. Now, I'm going to whet your appetite before you go. I want you to think about curves of constant r. Here are 2 curves of constant r. And I want you to think about curves of constant theta. Curves of constant r are circles. Curves of constant theta are rays, because they go through the origin and stop. Just as for Cartesian integrals, we looked at curves of constant x and curves of constant y, and we used those to chop up our space into rectangles. So too for polar coordinates, we're going to consider curves of constant r and curves of constant theta to chop up our space into these arc segments of the annulus. And that's what I'm going to do on Friday. So if we know the sizes of these little guys, we can figure out how to calculate integrals using polar coordinates. Now you just got to ask, why would we want to do that? When would we want to do that? How does that help us?